feedback as well. Oh, okay. Very good. So a couple of things. Yeah, so this has been recorded. So if you don't want your face recorded, turn off your video. I'll upload this maybe to YouTube somewhere publicly as well, if that's okay. So a couple of things. So one, I just set up a Discord server. So let me just get the link to that. So I'll put that in the chat. I'll circulate this afterwards as well. But I suggest if people want, you can just join this Discord server. Discord is just a way that we can chat around this. So maybe I can just put the links in here. I can say, here's where the videos are in the future. And maybe I can make a little channel on it that, say, for suggestions that people just want to post in, oh, I'm interested in learning about this or something like that. So yeah, put that in the chat. You just click on that, you should be able to join it. Okay, so some people are in anyway. Very good. So that's the Discord. Yeah, if you've questions throughout this, let me close this. If you have questions during this, then you can just put them in the chat. Maybe rather than just interrupting, you can either wait till the end and turn on your video, or you can just put them in the chat. Very good. Let me see. Okay, and then I'll try put any of the code I do, I'll put them on GitHub, just on my my GitHub here. So if you just search for, I think it's just GitHub, Philip Cardiff, 1L in Philip. And then there'll be a repository called, I just created OpenFOAM coding recurring short training. So there's nothing there at the moment, but I will just put the stuff in there. And if I make commits, then you can go back through the history of any changes I was making. Okay, I'm going to use OpenFOAM 2412 for this. If you've used OpenFOAM, you might see there are different variants of OpenFOAM. Essentially, there's openfoam.com and .org, and they are somewhat diverging in recent years. And there's also Foam Extend. But broadly, the underlying coding is the same in all of them. All right, so I am loading OpenFOAM 2412. I have an alias set up just to load the various different versions. And then doesn't matter where you put any of this code, if you want to follow along or afterwards, looking at the videos. I normally just go to run, and then I go back one directory, and I keep stuff here, like I've solved for foam here. So I'm just going to download this repository, which is just empty, git clone. So I'll just put all the stuff inside this just to keep it in one place. So one code in training. Very good. All right, so what am I going to do today? So I've lots of ideas for the coming like months, weeks, and you probably have suggestions as well, but probably just as somewhere to start, just to make one utility to do something. So I'll just take an existing like basic solver, laplacianFoam, and I'm just going to change that from the Laplace equation to the wave equation, and then just tell you some things about how to read things in and out of OpenFOAM and change like on the fly between some settings. So that seems reasonable for a first kind of 30 minutes. But in the future, probably going through some coding to do with the mesh object and time object and field objects, and then towards boundary conditions, thermophysical models, etc., etc. So that's the idea. Okay, so I have nothing here. What I'm going to do first is I'm going to take a copy of the OpenFOAM solver called laplacianFoam. So in OpenFOAM, there's, when you load it, it defines loads of these environment variables. So if I go echo $foam underscore, and then I go tab, it shows me loads of these things. So if I go foam solvers, you can see this is the location of where the solvers are, foam tutorials, etc. So I'm going to go copy foam solvers /tab. Let me get rid of my face here because I can't see. Okay. Solvers tab, and then I'm just going to go basic tab, and then laplacianFoam, and I'm just going to copy that to the current directory. So you can see I've laplacianFoam now, but I'm just going to rename this. So to make my first solver, I'll rename it to my test foam. So I've just renamed the folder to my test foam. So my test foam, go inside it. Move this thing out of the way. Okay, so this is the guts of laplacianFoam. So I'm just going to delete a few things I don't want. So there's this over Laplacian foam. That's just a overset version. So I'm going to ignore that. So I'm just going to get rid of that. So essentially I have laplacianFoam.c, and I have a create fields file, and I have a write.h file. And then there's a make folder or make directory. Inside that make directory, there's two files and options. So the make folder contains instructions for compiling this solver. And inside that file it says what to compile, and then options are just options related to that compilation. So what I'm going to do is rename laplacianFoam. I'm going to rename that to mytestfoam.c. By the way, when I type ls, I've set up an alias that's actually ls-al H or G or something like that, just to color it and make it easier to see these things. So I've renamed the solver to mytestfoam, and then I will open make files, and this says what should be compiled. So instead of laplacianFoam.c, which doesn't exist, I'm going to change it to mytestfoam, and then the list of files to compile are at the top, and then the bottom here is what the executable will be. So when you compile the code, what the actual executable will be. So I will call it mytestfoam without the C. So in OpenFOAM, solvers are always end. The style convention is with the word or the subscript foam. The other thing is for any custom code, rather than putting it in the foam app bin directory, which could be read only if you're on like a supercomputer system or a system where you're not the admin. So it's better to put it in user. So foam user app bin. So that will be a directory in your user folder. And so typically, if you're making any code for OpenFOAM, you put it in foam user app bin, or if it's a library, it'll be foam user bin. All right, save that. So just to check I didn't break anything, I'll first go wclean, that's just to clean the build, and then wmake, which will compile it. So wmake is just what's called a build script. So it will read what's inside this make folder, which basically says compile this mytestfoam.c, and then it looks at the main OpenFOAM installation, what settings are required to compile OpenFOAM code, and then all it does is essentially just copies and pastes the big compilation code, compilation command. So in this case, on my computer, I'm using a compiler called Clang++, or C language++. Most, if you're using Linux, you're probably using GCC, that's fine. But essentially, that's all wmake does. It generates this command with all these options, so you could actually paste that in yourself to do it, but there's no need to do that. So wmake is an OpenFOAM specific one. Make and CMake are more general popular ones, but OpenFOAM made their own one. Okay, so it compiles mytestfoam. Let me open a second terminal. I'll load 2412 in this. I'll move back up a directory. So I'm just going to get a test case. So let me just copy a test case from the tutorials. So foam tutorials /basic tab, laplacianFoam tab. And there's one called here called flange. So I'll copy this. So once again, I'll rename this flange to just my test case. Oh, my test case. So it has a bunch of scripts. So I'll just run the all run script first, just to get the run to see what happens. Okay, I'll cancel that. I'll open the case in PowerView. So on my Mac, I have a shortcut set up for opening PowerView, but you can open up PowerView whatever way you normally do. So this is just the default flange case. It's some sort of, I don't know, engineering bracket or something like that. And it's solving the heat equation, so Laplacian case. So I don't know, it's hot inside and then the heat spreads everywhere. Okay, so let me just run the all clean script. Okay, I'm just going to get rid of a bunch of things here. So I'm going to get rid of these all clean scripts, all run scripts. Let me see. I will move this 0 original to 0. Well, if we go inside it, T. Okay, so that mesh is kind of complicated. So I just want a really basic mesh for someone for kind of practicing when we switch this Laplacian equation to a wave equation. So I am going to copy from foam tutorials, incompressible icofoam cavity. So one of the first tutorials you do if you start with OpenFOAM is this icofoam cavity case. So it's a flow inside an enclosed cavity. And it uses block mesh to make the mesh. So I'm just going to use that instead. So I will just copy that to system and run block mesh. I'm not going to go through the details, but if I check the mesh now, it's just it just looks like this. So it's like a fixed wall, fixed wall, fixed wall, and a moving wall. But okay, I'm not going to do a flow simulation here, but I'm just going to use this mesh. So inside 0, I just want to update the boundary conditions. So I just need to change the names of the patches. So I think the top one is called moving wall. I'm just going to set up some test case to begin with. It doesn't matter too much. I'll say the top wall is 100. The starting temperature is 0. And then I will change the side walls, I think are called moving walls. I'll set those to be 0. And then I think the last thing is at front and back, and they're empty. Okay. I can check this in constant polymesh boundary. That's the actual mesh. So moving wall, fixed wall, front to back. Yeah. Okay. Very good. So if I try run laplacianFoam in this case now, what's the problem here? Cannot find fixed walls. So, oh, moving walls. Oops. So moving wall and fixed walls. Okay. Okay, so if I run that now, generates all these time steps. Let's have a quick look. So we said it was hot on top, and then if we run it in time, okay, so it's just like a heat conduction problem. So it'll go to steady state, that it just spreads out over it in some way. Very good, not too exciting. Let me just delete some of those results. Okay, so that is that. But if you remember, we compiled our solver called myTestFoam, even though we didn't change the code. But if we run myTestFoam, it'll just do exactly the same thing laplacianFoam did, because it is just laplacianFoam, and we just renamed it. That's fine. All right, so let's change some code. So I'll open one more terminal. So I'm going to have 3 terminals open. I'll have one terminal where I will open the code just for editing it, and then I'll have one for compiling it, and then I'll have one for running it. Okay, so the first thing, if I go inside any OpenFOAM code, you'll always have this copyright. So this is actually, well, they're strictly following this GPL license. I don't know if they actually need to put in all of them, but this is what they do. So that's fine. I strongly suggest that if you are writing code, that you comment it as you write it, not afterwards, because I have not met a person yet who will, once they get their code working, go back and actually add comments. So either you do it when you're writing it, or just accept that you won't remember what you did in your code. And so I'll just update the top here. I'll just say my test foam. I'll get rid of this little group, and then I'll get rid of all these details about the laplacianFoam and just say, this solver is for testing out OpenFOAM coding skills. And you might as well add your name as well. So I'll add my name. Okay, so if I go down and look through this code, so this is the laplacianFoam code that I've now renamed to my test phone. So there's a few things. This is C++, even though OpenFOAM is C++, but it's technically a domain-specific language. So it's C++, but they don't use very much default C++. They tend to redefine their own functions for everything. And there were some historical reasons for that, and there's some efficiency reasons for that. You can use C++ code, but you'll see a lot of the functions maybe are not described generally online. They're only in OpenFOAM documentation. So there's a few things here. There's this arglist node. It adds a note what it does. We don't really need that. There's some other things we don't really need, but I'll kind of skip over these. Most utilities or solvers in OpenFOAM will have this sort of stuff at the start. Mostly it's just to read some default settings out of an OpenFOAM case. And maybe here's to create the mesh. And by create the mesh, it really means just to read the mesh from disk. And one other thing which we will edit a bit is there's a file called create fields, and we saw that was in the case. We saw this create fields here. So normally in OpenFOAM, if you have a solver, if you're reading fields or reading dictionaries or reading anything from the case, you do that inside a file called create fields. That's just a kind of style convention. And just to point out, hash include, when we compile the code, when the compiler sees hash include, it just goes and finds this file and it essentially just copies and pastes it to be here. So if I wanted to add a new file, I could just say my new file.h, and if I put my new file.h in the directory here, then it will just include it when I'm compiling. So if I loop down here, we'll see it prints out info calculating temperature distribution. There's this loop, this simple.loop. And so this is essentially looping through the time steps. There's an extra loop inside this non-orthogonal correction loop. Then it makes this t equation, this Laplace equation, which is the time derivative temperature minus the Laplacian of temperature is equal to 0, or equal to the Laplacian, and then this other thing here, and then it solves it, and then after it solved it, then it goes hash include this write.h, which we saw here, and here it is. So that does something to do with post-processing, and then it prints out the execution time, and then it's done. Okay, so there's a few things I don't really care about or want here. I can probably get rid of this non-orthogonal loop because my mesh is not non-orthogonal here. I'm only testing. This FE options is just at runtime you can add like on the fly different source terms or complicated methods, but it's 0 at the moment, so I'll just turn that off as well. Instead of minus, I could go equals here, like in the kind of standard maybe way of writing like a kind of Laplace or Poisson equation. I'll get rid of these FE options things you don't need either. And yeah, so if you make any changes in the code, it's normally good to compile often because then if you break something, you very quickly know what was causing the break rather than writing a load of code. Very good. So that's our TTT equation. Yeah, so what do I want to do? So if this is called the Laplace equation, which represents things like diffusion processes, if I change the left-hand side here to a second derivative, this represents a different physical phenomenon. So this is the wave equation, it's called. So normally we'll write this with a variable called c squared here. So if c is the speed of sound or the speed of the wave, then you normally write this where c squared is the square of the speed of sound here. So the cool thing with OpenFOAM is I can just use this second time derivative operator, run it like that, and everything's fine. So actually this probably will compile, but it won't run. And I'll tell you why it won't run in a second. Oh, of course, actually it won't compile. So I've added something called c squared, but the compiler is basically saying use of undeclared identifier c squared. It doesn't know what c squared is. So where was that TT calculated? So if I go into create fields, you can see it creates a T field. And there's something called DT. So what they're calling DT is D is the diffusivity for T, which is temperature. So they actually have it as a field here that you could actually, it says read if present. So without explaining all of this, it basically will read it from the time, which is like 0. But if it doesn't find it, it will look up a file called transport properties in the constant folder, and it will read DT from there. So if I go to the case, I go constant transport properties, this is just where that number is being read from. But okay, I don't really care about DT being DT being a field. Actually, I don't even want DT anymore. I'm just going to read C, the speed of sound. Speed of sound. I'll get rid of all this stuff here. So what do I want to do? So first thing to notice here is this piece of code here, transport properties. This is the way you create something called a dictionary or an input-output dictionary in OpenFOAM. So even if you don't understand what's going on here, if you wanted to make another dictionary called my properties, you can just like rename things here. And you can see that it's trying to read it. And then this must read if modified, okay, that's fine. So I want to read something called C, which is my speed of sound. So I'll go C, actually, I will make it a dimension scalar. C, and constructor, I will read it like div viscosity and then C. Yeah, okay, like I'm gonna make something called C here. Okay, these FE options, I don't need that either. So the dimensions here are wrong. So OpenFOAM has this dimension checking. So it's just to stop developers making fundamental mistakes in their equations. So that you can't add something that's meter squared to something that's meters per second, for example. So my C is going to be dim velocity, speed of sound. And this is the way to define something It has a little name that it's going to look up from this transport properties, so this dictionary here, and then it's going to have these dimensions. So let me just check that compiles. But before that, I need make something called c squared. So c squared is just going to be square c. So there's an operator in OpenFOAM called square. I could just go c multiplied by c, but it has an operator called c squared, and that will work with tensors and vectors and things like that as well, with appropriate operators. Let's see if this compiles. Okay, so you can see now in the write file, it's trying to use dt. So I didn't look at that write file yet, so I actually don't care really about that write file, but let's look inside it. Okay, so it's calculating the gradient of this t and then some other things. So I'll just get rid of, it's calculating dt. I think that's the heat flux, but okay, that doesn't make sense anymore. So I'll just get rid of all that stuff and compile again. So I'm just looking up this c from transfer properties, and then I'm defining c squared like that. Okay, that compiled. And then if you remind you what our solver looks like. So it looks like this. Okay, so now if I try run the case, my test foam, OpenFOAM will say entry C is not found in this dictionary. And if you look at what this dictionary is, it's constant transfer properties, which makes sense. So constant transfer properties. So if I go here, instead of having dt, we should have c now. And okay, you can set to something physical, but I'll just set to 1 meter per second for now. Okay, so now we got a bit further. So it's saying entry d2 dt squared dt is not found in system FE schemes second time derivative. So if I open up system FE schemes, so system FE schemes is where the discretization methods are defined for the terms in the solver. So we have two terms. We have a second time derivative and we have a Laplacian. And there's different ways that the final volume method could discretize these. So they are selected at runtime when we run the code, and that's defined here. So you'll see we don't actually have a second time derivative settings. So I'll just set the default. Euler is this first order method in time. So that's fine for now. So let's try this again. Okay, next part that says Laplacian c squared is not found in the Laplacian schemes. So I'll open up that again. You'll see that, okay, I just need to change this to be this. And it's using this Gauss linear method to do that Laplacian. Okay, something happened. I think not much exciting will happen here, but I probably need to change the time steps to be smaller. Okay, so the one thing to note is the answer here will actually be the same in the limit where you go to a large t. So when this term goes to 0, you basically just get the answer to Laplacian equals 0, which would have been the same previously. But what happens in the transient will be quite different. So let's just make the time steps a bit smaller here. So instead of 0.05, maybe I'll go to e to the minus 4. I'll maybe run for 0.1 of a second, and I'll write every e to the minus 4 as well, let's say. So I'll delete the previous results, run this up onto that time, go back to here, skip. So if I play it now, oh man, my time step's too small, is it? Okay, I'm probably writing out too many time steps. So instead of writing every 1 e to minus 4, I'll just write every 1 e to minus 3. And we delete these and run the case again. Oh, relax. Yeah. So if I play this now, you'll see something like this. So it's actually like a wave propagating out that bounces around. So that's fine. Just to show something else, a couple of other things. I'm actually going to, rather than have high value here, it's for a wave case, it probably makes more sense if we just start with an initial non-smooth field and then run the case like that. So I'll set the value to be 0 everywhere. And then I'm going to use a utility called set fields just to set a high value in the center. And then we can watch, like, it could represent a value of high local pressure and then low pressure everywhere else, and then it'll cause a pressure wave to travel out. Or it could represent like a little piece of high water or something like that, like a little dam, and then that will collapse and bounce out. So to do that, I will gonna run a utility called setFields, but I need some settings for that, and it expects a setFields dict. So I will just find an example of one of those. So I'll go find in the tutorials something called setFieldDict. So there's loads of them. I'll just take the last one, and I'll put that in my system folder, systems setFieldDict. So the way it's set up is you can say, here's the default value for the field, my T field 0, and then there's lots of different methods you can use to initialize values. So I'm going to use one just that is box to cell. I'll get rid of all these other things. So box to cell, and I can't exactly remember the settings for this, but we'll find it out in a second. And inside box, I'm going to set the value to be, let's say, 100. I think I need to specify the lower coordinate and the upper coordinate. So I think this cavity case goes from 0 to 0.1. So if I go 0.04, 0.04 to -1, and then maybe 6 plus 1. So what am I doing here? We'll find out in a second if that's correct. I'll make a backup of the 0 directory because this is going to overwrite my T field and fill it up with values. So I'm just going to make a copy of that. So if I go set fields, okay. So you can see it says adding cells with a center within this box by the bottom corner, top corner, 16 cells, setting those values to 100. So if I go back to here, I'm basically setting the values there. So if I actually, just to visualize it differently, if I slice through it, and then if I use a filter called warp by scalar, I could move this surface in that direction by the value of the T field. Just for visualization, this could be kind of useful. Okay, so this could represent an area of higher pressure or like an initial little piece of water that then collapses. So then if we start that and we solve this case, so my test phone, that was quick. Maybe we didn't print out enough time steps. Let's see. So if I solve this in time, okay, that actually would have been more useful to have more time steps that time. So let's write out more time steps. Okay. So if I play it now, oh, did I refresh that? Oh, that's very quick. 10 time steps. Did I change the right thing there? Why is this not seeing the time steps? All right, I'm just going to open it up the second time in Purview. That's better. Okay, let me do that again. So this one seems to see all 1,000 time steps. And I will go filters or by scalar and maybe it was a 5 or something like that. Okay, cool. So if I play this now, yeah, okay, now you can see it a little bit better. So this is solving the wave equation, so it's like this high pressure then travels out at a certain speed, and you can see the waves bouncing around. And yeah, if I increase the mesh resolution, you can make kind of cool looking images and animations with this. In fact, it's probably actually very coarse at the moment. So if I just increase the resolution to be, instead of 20, maybe 100 by 100. We don't write quite as many results out. Oh, and I need to reset fields. So if I reset the T field, so the T field has been initialized. Oh, okay, excellent. I've accidentally deleted my T field. So my original one. So basically when I ran set fields here, it was setting all these values. And I thought I kept a copy, but I obviously deleted it. So that's unfortunate. So let me just manually delete these and then manually keep a copy of P this time. So if I go set fields this time, and then my test home, and then if I open this up now, yeah, the mesh should be a little bit finer. You can probably see what's going on a little bit better. Yeah, okay, that looks a bit clearer. So you get like this wave bouncing out and hitting off the walls and then coming back in, etc. Very good. So it looks cool. You can make lots of nice animations out of that. So then the last couple of things, I'm over half past, but I'll probably just spend 5 more minutes to do a little bit more in the code. So one thing which is cool in OpenFOAM is this FVM and FEC. These are finite volume matrix, or sorry, finite volume method. And then there's something called FEC, which is finite volume calculus. So those phrases don't necessarily mean anything to you, but essentially, if you have an FEM, that operator will create a linear system. So a matrix and a right-hand side. So both of these are creating things that go into a matrix and a right-hand side, and that means that when you go dot solve, it is actually solving a linear system. But if I change this to FEC, so this is still a matrix linear system, but FEC is just do a calculation and get the values. So that will be just like a right-hand side. So that means you could actually implement and switch to just an explicit implementation rather than an implicit one. So the matrix that comes from a time derivative, at least in finite volume method, is diagonal. So it means it's like a trivial linear system that can be solved just by dividing across by the diagonal. So if I change to that and recompile it, I'll get an explicit version of a finite volume wave solver. So if I delete all these results and let's see what happens. I don't know if the time step is small enough or not. So an explicit solver for small time steps will be faster anyway. Okay, we didn't really notice much down there. So if we saw this, so we should, in the limit of a infinitesimal mesh and an infinitesimal time step, they'll give the same answer as an implicit method. But I guess you might notice that there's this high frequency noise. So explicit methods tend to create dispersion errors, which means they tend to generate noise, whereas implicit methods tend to have diffusion errors, which means they tend to remove energy. So one tends to add energy, one tends to remove. Both are not good. But controlling those is part of appropriate selection of mesh and etc. etc. So then you could, if you're familiar then with, they're both first order in time, but you could actually go 0.5, 0.5. So half of implicit and half of explicit, and that this method is known as Crank-Nicholson. So you get Crank-Nicholson method, which is I think equivalent to trapezoidal rule, so that'd be second order in time. So if we were to run that, it's not bounded, so you might still see some noise, but it will be second order accurate as the mesh is reduced in time. Yeah, so it'll be smoother. It kind of shares the characteristics of both implicit and explicit. So it is an implicit method because you have to solve a system of equations, but it's more accurate in time. So then, yeah, the last thing just to show you to finish today is, well, that's kind of cool. Wouldn't it be nice if we can just switch on the fly in the case between the methods? So how about we just add a flag called implicit? So if implicit, let's do this. Else it's explicit. And if it's explicit, we'll go back to the explicit way of doing it. So the explicit way of doing it was this one. It's actually, you don't, for normally, if you look at real OpenFOAM explicit solvers, they normally don't create this thing if it's going to be explicit, because there's no point making a diagonal matrix. You can actually just manually solve it. So if it's an explicit method, you could actually just write as t equals t dot old time. That's a second derivative though. So it will be minus 2 times, so it'll be plus 2 times this minus t dot old time old time. So the cool thing in OpenFOAM, you can see you can get access to the old times, and then plus c or yeah, plus this thing basically. So that's all that's doing. It's just updating the current t based on the old time and plus the difference of the Laplacian. I think that's correct. You can actually check that if that works. Anyway, I'll leave it the way it is here for now anyway. So that's the explicit. This is implicit, but it's actually correct Dickinson, so this will be more accurate time. So okay, if I try to compile that now, it will say, oh, I don't know what implicit is because you haven't told me what that thing is. So it says, don't know what that is. So on the OpenFOAM convention, we'll go into create fields. And we already have a transport property, so let's just look it up from there. So we could look up something called a bool, but OpenFOAM has something more convenient called a switch. So switch is a generalization of the bool. So it can be 1 or 0, true or false, but it can also be yes, no, on, off. So it will take care of whatever way you say yes or no. So that's kind of convenient to have. So I can go implicit, and I can do it the same way again, but another way to do it is I can go transfer properties dot lookup. And there's a few functions that a dictionary has. So lookup is one. So I can say lookup implicit. So if I do that, it will define a switch that it'll look it up from this transport properties. So if I try to run the case now, it'll say entry implicit is not found in transport properties. And so I can go implicit, yes, remove results, and then rerun a test form. So I can see it's running implicit. So you'll notice one thing, implicit is writing out these residuals and how many iterations it's taking. But if I go back and set implicit to no, and then clear everything and run again, and you can see it's actually printing out 0 residual, no iterations. It's because the linear solver is trivial. It's just inverting the matrix. So it's not actually inverting the diagonal. It's not actually solving anything. So it's using a diagonal solver. So there's basically no point in making the system in that case. So you can see that's nice. And one other thing you can see, you can make it kind of easier to use. So you will have seen that we have info statements, so to write to the screen. So this is important when you're debugging things. But let's say we just want to do some sanity checks. So let's say that if C, which is what's called a dimension scalar, so that means it's a scalar, which is just like a double float, but it also stores its dimensions. So if we go dot value, it just gives us the actual number. So if that's less than 0, then that doesn't really make sense. You can't define the speed of sound as negative. At least this physically doesn't make sense. But actually, numerically, speed of sound as 0 doesn't even make sense. So probably less than some small number. So OpenFOAM defines something called small and v small. So it's just built in. So I think small is 1 e to the minus 15, I think. So let's say if it's less than that, we could use something called a fatal error. So I can say C C should be positive. And then you go like this. So you go abort, fatal error. But else, let's just do another check just to show. So else if C dot value is greater than, I don't know, 1 e to the 15, that just sounds crazy. So let's say, maybe it makes sense in some case. Let's give, not an error, but in that case, we give a warning. And then otherwise, we'll say info C equals C dot value. So all I wanted to show here is there's 3 ways to send messages to the screen. You can use an info, you can use a warning, or you can use a fatal error, and you can see the effect of each of those 3. You can use std cout. This is the standard C++ way of doing it. Why would you not do that? Well, when OpenFOAM runs in parallel, that may have unintended consequences. You may have all the processors writing or not. So let's say info, warning, and fatal error are all parallel aware. So this is this point about OpenFOAM kind of redefining commands to make them OpenFOAM aware. So let's compile that, see if it works. Great, works. So then let's check. I'll open another terminal here, just open up the transfer properties. So instead of using 1, let's set it to -1. Try my test form. So it says, you can see, oh, that's the wrong one, this one. So you can see it says fatal error, C should be positive, and makes sense. Let's set it to 1 e to the 22, In this case, it says C should be positive. Oh, did I copy the exact same message? Yes, I did. So C seems a bit large. Okay. Oop. And then compile that again. And oh, sorry, this abort. You shouldn't put that abort. I just copied without that looking. So okay. So it should just be an end line. When I recompile that. So then it'll actually just print a warning. And see if that compiles. Yeah, and oh, delete the results. Yeah, so actually in that case, if I jump back up to top, you can see it just prints a warning, but it actually keeps going. So because I'm using an explicit solver here and I've set the speed of sound very high, it actually just explodes because I would have to have a very, very small time step for it to be stable. And then if I set it to be maybe 1 back to 1 or whatever, then we saw that it should info out the value up the top here. So it says it prints out equal done. Very good. Okay, I think that's fine. I've gone on a bit. So I will stop sharing and I will stop the recording and